And he, oh, I see that. It's great. It starts with a friend of mine whose name is Ahmad. And he actually, I think he's in Brazil now. It's been a little while since I've talked to him, but he was a grad student at Cornell. He was a year older than me. Back then, the math common room was kind of fair game for undergrads to go and chill in. And he had this question for me, which kind of, the more I thought about it, the more it kind of blew my mind that we couldn't answer it. So it went something like this. All right, so suppose that I take, so Q is the irrational numbers, is the rational numbers. And what I want to understand is something about the interval from 0 to 1. So if I think about Q intersect the interval from 0 to 1, so this is all rational numbers between 0 and 1. Whoop. What is going on? Is that just, okay. Between 0 and 1. There's a very natural way to enumerate them. And the way that I want to enumerate them is just to go in terms of increasing denominator. So let's suppose that I list these out and they are 0, 1. So I think about the, nobody's home. Just a sec, sorry. Sorry about that. Okay, hopefully there's not going to be any more interruptions. So suppose we list these out, 0, 1, 1/2, 1/3, 2/3, a quarter. And obviously I'm not going to write 2 quarters because that's already 1/2. So we're only writing them in simplest form, 1/5, 2/5, and so on. Okay. So let me call these numbers Rn, where I think about n as just sort of the enumeration of them. So these correspond to 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the first 9. And what I want to do is I want to write, so for each of these n's, I'm also going to write Wn, which is going to be the following. It's just going to be 1/3, 1/3 squared, 1/3 cubed, and so on. So I'm just going to write 1/3 to the n. So the problem is the following. Look at the interval from 0 to 1. So I'm just going to draw, there's my interval from 0 to 1. And what I want to do is I want to just think about these numbers. So here's the first one, 0. And what I do is I want to erase the interval between 0 and 1/3. So I look at the interval which has total width 2/3, really, but centered at 0. So somehow this interval. And I think about this as, this is going to be I1, the first interval. And I go to the next one. So I have R2 is 1, and I remove an interval of width 1/9. So that will be something like this. So I remove this interval, I2. And then I go to 1/2, and now I remove a tiny interval where the endpoints are, so this upper endpoint is 1/2 plus 1/3 cubed, 1/27. And this lower endpoint is 1/2 minus 1/27. Okay. So this is I3. And I do this for all of the rational numbers. And there's going to be overlap. So already when I'm at I4, I4 is completely contained inside of I1. It's some interval. Oh, that's not quite true. Sorry, I'm thinking about which one am I thinking about? I6. So there's, there's an I4 and there's an I6. There's an I5 and there's an I6. Okay, so I have all of these intervals within the interval from 0 to 1. And what I want to do is I want to erase them. So I want to remove all of these intervals. So remove from the interval 0, 1, all of these INs. If I think about the total length that I've removed, so that's just going to be the sum of the lengths of the INs, which is the sum of, and the length of IN is 2 over 3 to the n, right? It's an interval where I have some rational number, I go 1 over 3 to the n to the right and 1 over 3 to the n to the left. And if you know about geometric series, this sum from n equals 1 to infinity is just equal to 1. But not only that, that means that, some of these have overlaps. So what that means is that there must exist a number x in the interval from 0 to 1 such that x is not contained in IN for all n. Right? Because the interval from 0 to 1 has length 1, and we're removing something where if we summed up the total lengths of all the intervals, we got 1, but some of these intervals lie outside of our original interval, and some of them overlap, so we've removed something of total length less than 1. And this, to me, is already something rather counterintuitive. So if you haven't seen this before, yes, I will be careful using the exclamation mark for n here. For all n, I'll draw a smiley face. Okay. Where the smiley face is not mathematical notation. It's just happiness. So yeah, so this is already surprising. If you think about what's going on, we have that, we have this interval from 0 to 1, and we're removing all of these little intervals from it. So we've removed all of these intervals sort of going along. And we've done it in such a way that we've removed all rational numbers. If the smiley face is rational is mathematical notation, then I'm definitely reading whatever paper that's in, is what I'll say, Joy. So, okay, so we've removed all of the rational numbers. And so it's kind of bizarre. We remove these intervals that are getting smaller and smaller. They kind of seem to cover the entire interval. But the fact that they're getting small so quickly means that there are some numbers that are going to be left over. And that's super counterintuitive and makes you think maybe a little bit differently about what the real numbers are. To me, at least, this really does. So there's a motivating question, though, and this is what my friend Ahmad asked me. He said, what is an example of such a number x? Right, so we know that these x must exist, or at least maybe you believe me that these x must exist. If you've taken a real analysis class, then you can prove that such a real number x exists, if you like. And the question is, what is an example of such a number x? So does anybody have anything that they want to maybe guess is some number that they might expect to show up in this, that's not in any of the INs?
Maybe an irrational number?
Yeah, so at the very least, so it must be irrational. Ooh, I see. Okay, that's a particularly good guess, Matthew. So it must be irrational. And there's a suggestion of, I'm going to write it this way, 1 over the square root of 2. And I claim that this is an example. So this is an example of such a number. So how do you prove something like this? Okay, so proof that 1 over square root of 2 is not in in for all n. So let's think about what we want to show. What does it mean? So suppose, by way of contradiction, that 1 over root 2 is in in for some n. Then what happens? Well, what that means is that there's some number. So if I look at that Rn in that enumeration before, I can write that rational number as Pn over Qn. And we're just saying that 1 over root 2 minus Pn over Qn is less than or equal to 1 over 3 to the n. So, so in some sense, this would mean that 1 over root 2 is approximated really, really closely by this rational number. So now let's think about the function y equals x squared. So here's the function y equals x squared. And let's just consider it from the interval, on the interval from 0 to 1. So I have these two numbers here. I have 1 over root 2, say is right here. And say I have my Pn over Qn, or Rn, is right here. Then when I look at their corresponding squares, so I get 1/2 and I get Rn squared, notice that the slope of this line, so the slope of this line connecting these 2 points, is less than or equal to 2, right? Because the derivative of x squared is 2x. So on this interval from 0 to 1, it's never going to be larger than 2. In other words, what that means is that this inequality tells us that when I square 1 over root 2, it's again really close to Pn squared over Qn squared, but such that the difference is now less than twice of what the difference was before, 2 over 3 to the n. So now,
shouldn't this slope be greater than or equal to 2 rather than less than or equal to 2?
No, so it's less than or equal to 2 because the largest slope that you can possibly have comes from the tangent line at x equals 1. And here, y prime is equal to 2. Great, good question. Thank you. So now let's look at this inequality. Looks like we haven't made much progress, but the thing that you'll notice now is that nothing is irrational. And since nothing is irrational, what that means is that we can multiply out by 2n Qn squared to clear denominators, and we find that Qn squared minus 2Pn squared is less than or equal to 4 times Qn squared over 3 to the n. Now let's think about this quantity, the absolute value of Qn squared minus 2Pn squared. So first of all, clearly it's an integer. Secondly, since square root of 2 is irrational, this number is non-zero. So now we see that we get a little bit of extra juice because this number here must be at least 1. So in other words, What that means is that we must have that 3 to the n is less than or equal to 4 times qn squared. Okay, well, let's go back to our list of these numbers, right? And let's think about this. We have that qn, if we just look at qn here, so I think I'm still, no, I'm not. So if I just looked at qn, just the denominators, I'm thinking of these as 1, 1, 2, 3, 3, 4, 4, 5, 5. So they're not growing so large. In particular, qn squared also isn't growing so large. Meanwhile, 3 to the n is growing massively, right? If I looked at 3 to the n, this is 3, 9, 27, 81, and so on. So it's the case that unless n is equal to 1, this inequality doesn't hold. So this inequality only holds when n equals 1. But now you can just check that 1 over square root of 2 is not in I1. So in other words, 1 over square root of 2, just because we said that we were supposing it was in IN, we showed that if it's in IN, it must be in I1, but it's not in I1. This means that 1 over square root of 2 is not in any of the intervals. So this implies 1 over square root of 2 is not in IN for all n. So that's the proof. And when I saw this, I was pretty amazed, I'll be honest, because I think in the first place, when I first saw this proof, it was that my friend Ahmad had come up with it himself. So we had discussed it for about a week. I didn't hear about the problem for, maybe two months. And then he came back to me and he said, I have a solution. And, he showed me this and it was just amazing somehow that you could get just by a little bit of sort of geometric arguing. The only thing you need is just to take a square basically so that you get something rational. And that gives you this extra piece of information where you can multiply out and get this integer. So it's not just non-zero, but it's bounded by 1. That sort of gap between 0 and 1 lets you say something extra. And I just think that that's a really, really beautiful idea. And it's an idea which really is at the start, at the foundation, as I found out later, of what would now be called transcendental number theory. So, if you look at this proof, then actually there's a proposition which is sort of more natural to state. As you'll note, I started with sort of this enumeration, and then the key last step was that, okay, well, this 3 to the n is always less than or equal to 4qn squared. But what you should instead think is that really what we've proved and what's more fundamental is that for any p over q, a rational number, we have that 1 divided by the square root of 2 minus p over q is greater than 1 over 4 times q squared. Okay. That's really what we proved, not just that, that this difference is greater than 1 over 3 to the n, where n is the number that appears in the enumeration. Really, it's something intrinsic to the rational number itself. I write it as p over q, and I get some bound. I get that this approximation is bad in a sense, which is in terms of q squared. So in some sense, this is a result saying that 1 over root 2 is not well approximated by rational numbers. Right, it's a quantifying way of saying the statement that 1 over root 2 is not approximated well by rational numbers. Okay. So you might ask, what other sorts of quantities, satisfy similar bounds? So for example, if I gave you 1 over root 5, can you also say this? And the answer is yes, but with a different constant. So instead of 1/4, you would have some other constant, which depends on the fact that I'm taking 1 over root 5 instead. But the proof basically doesn't change. And to see this, we can define algebraic numbers as the following. So an algebraic number is some number alpha in R, satisfying some polynomial, some integral polynomial equation of the form f0 plus f1 alpha plus up to fd alpha to the d equals 0, where the fi's are integers. Okay. And fd is not necessarily 1. I'm not saying that at all. So if d is the minimal such d is the minimal such degree of a polynomial, we say alpha has degree d, or is algebraic of degree d. And if alpha in R is not algebraic, it is, much like the great philosophical thinkers of the late 1800s, said to be a transcendental number. So these are the numbers that had a cabin on Walden Pond. Okay. So let's see. Example. So a quick example of an algebraic number of degree 1. Degree 1. Algebraic number would just be a rational number, p over q. Because if this is alpha, then it satisfies that q alpha minus p is equal to 0. So it satisfies a polynomial equation of degree 1. An example of a degree 2 number would be something like, say, alpha equals 1 over square root of 2, because it satisfies that 2 alpha squared minus 1 equals 0. Anybody want to give me a degree 5 algebraic number?
Fifth root of 5.
Great, the 5th root of 5 sounds great. So if I take alpha to be equal to the 5th root of 5, then it satisfies that alpha to the 5th minus 5 is equal to 0. And a transcendental number well, this is an interesting question. Nowadays, we know a number of examples. So nowadays, we know, for example, that E and pi are both transcendental. But okay, you know, how do we know that how did we first figure out, right, I see that, what's the general form for a degree 2 algebraic number? Yeah, exactly. So Ajmain's whatchamacallit, reply is correct. So any a plus b square root of d for a non-squared d, where a and b are rational, are true, are exactly that. And the reason why is because if you think about it, they're just any numbers which satisfy a quadratic equation that aren't already rational. And so by the quadratic formula, you always get something of the form a plus b square root of d. By the way, one often considers I itself to be an algebraic number because it satisfies I squared plus 1 equals 0. And so you can think about algebraic numbers as actually living within the complex numbers. And usually you do that because algebraically it's no different. So anyways, nowadays we know that e and pi are transcendental numbers. And if you know something about countability and uncountability arguments, then you can show that the number of algebraic numbers is countable just because the number of polynomial equations with integer coefficients is countable, and each of them has a finite set of roots. So at the turn, you know, in terms of early 1900s, sort of David Hilbert kind of inspired arguments and Cantor inspired arguments, people knew that transcendental numbers existed in abundance, that if you threw a dart at the interval from 0 to 1, in fact, almost all the time you're going to land on a transcendental in some precise sense. But in the 1800s, in 1844, it wasn't even known that there was an example of a transcendental number. And Legendre proved in 1844, so Legendre 1844, proved that transcendental numbers exist. By the way, Adrien-Marie Legendre, to speak in a terrible French accent, was a French mathematician. And my favorite thing about him is that there was a portrait of him that was used until 2005 when they discovered, so somebody realized that the portrait that they were using was not of the mathematician Legendre, but of a French politician with the same surname. And so now there exists only one portrait of this mathematician, and the portrait of the mathematician is very unflattering. He looks extremely angry. It's just his face, and it also includes a really unflattering picture of Fourier. So if you look up his Wikipedia article, you'll find it, and I encourage you to do that because it's rather funny, I think. I see that Joy has asked, did he prove this by showing one, or was it non-constructive? And the answer is that we're actually going to go through essentially his proof. So is this, maybe no. I think no. Yeah, exactly. So the existence of transcendentals, but that's a later argument. So the argument of countability and non-countability is, am I mixing up? I might be mixing up Legendre and Louville. So maybe I take this back. Okay, so I take back what I said about Legendre. I'm not actually sure of the person now. Gosh, okay, that's embarrassing. But the thing that I said about Legendre and the portrait is still true. But yeah, the proof of the existence of transcendentals by countability arguments. Countability didn't exist in 1844. And 1844 is definitely the year that transcendentals were proven to exist. So the idea is as follows. There's a proposition, or maybe a theorem, which is as follows. It says that if alpha is an algebraic number of degree d, then there exists a constant C alpha greater than 0 such that for all P over Q a rational number, we have that alpha minus P over Q is always larger than C alpha over Q to the D. So this comports with what we saw before in terms of, in terms of 1 over the square root of 2, which was algebraic of degree 2. We saw that we got some sort of non-approximation theorem by where we replaced D by 2. And so maybe I'll say that the proof of this is essentially just the same. Essentially the same. In the end, you have that f of alpha equals 0. And so if you apply f to, if you suppose that alpha minus P over Q, say, is, if I think about this, I can turn a bound on this into a bound on f of alpha minus f of P over Q using the derivative of alpha. And in such a case, I see that f of alpha is just equal to 0. And so I get, I get now some new bound on f of a rational number. And if I just multiply by Q to the D, that gives me an integer. So I again get this gap between 0 and 1. So I won't write up the whole proof, but this is sort of the basic idea. And and I leave it as an exercise, I guess, for you to fill in the details of why that's the case. So, it could be the case that, the cube root of 2 is better approximated by rational numbers than the square root of 2, because this theorem has it with, you would have D equals 3. Yes, the left is an exercise to the viewer, the best of all proof methods. But I think I've given enough that that at least you can be convinced that that I know the proof. Let's see. So yeah, so in some sense, this theorem is saying again, is quantifying that algebraic numbers are poorly approximated by rationals in some very precise sense. And what that means is that, this gives you a way to try to construct a transcendental number. So idea to construct a transcendental number. Cool. Number is find one which is very well approximated by rational numbers. And so it goes that Louville, which is why it should be Louville and not Legendre. I don't know what I was thinking, but okay. So Louville wrote down a number which is the following. If you write down the sum of 10 to the minus j factorial from j equals 1 to infinity. So this is equal to something like 1 over 10 plus 1 over 10 squared plus 1 over 10 to the 6th plus 1 over 10 to the 24th, and so on. Or in decimals, this would be 0.113456, and then lots and lots of zeros with a 1, and then even more zeros. So sort of these ones get spaced farther and farther out. What we see is that, if I cut off my approximation, say here, then that's a ridiculously good approximation for my number. And in fact, you can show that, so let's call this lambda. And the claim is that for all C and D greater than 0, there exists some n, a natural number, such that if I look at lambda minus the nth partial sum, so I only take up to n of 10 to the minus j factorial, and I think about this, this is going to be some number p, pn, divided by 10 to the n factorial. So this I think about as my qn. Well, this will be, less than c over 10 to the n factorial to the d. Just because the next digit which shows up is at the 10 to the n plus 1 factorial place. Yeah, exactly. So we're proving that something is transcendental by showing it's well approximated by rationals. So what this means is that, if you believe this inequality, then what that means is it can't possibly, so lambda cannot be algebraic, because if it were, we wouldn't be able to have this property. We would have some C and D, such that lambda minus p over q is greater than c over q to the d for all p over p over q. But we've just shown that that's not the case because a large enough partial sum gives us something which contradicts that inequality for any c and d that you chose. And therefore, transcendental numbers exist. So if you think about this, it's something like we had those intervals that we were removing from the big interval 0 to 1. And there's going to be a lot of them such that such that lambda lies within this interval. In fact, sort of infinitely many of them, such that lambda lies within this interval. And it doesn't matter how thin you take your intervals, even if it's 1 over q to the n for any n, you're always going to have that lambda is going to lie within that. So because lambda is super well approximated, it's a transcendental number. Okay. Any questions about that? Okay. So I'll make a remark. Originally, this was going to be a bigger portion of what I was going to say. But a remark is that, so maybe I'll make this a long remark, but you can ask what rationals best approximate a given number. So let's think about a number like pi, right? Pi is, I should write approximately because I'm never going to write out all the digits, but okay, it's about 3.14159 to, okay. Okay, so it's something. And if I think about this, you've already seen some approximations for it. So one of the first approximations that you might have seen is 22 over 7. Right. I see. So the answer to the question of Julian, so Julian asks, can any transcendental number be approximated by rationals, or does that only work for certain numbers? And the answer to that question is that it only works for certain numbers, and in fact, it only works for a really small portion of numbers. This proof. So if you know about measure theory, then the set of transcendental numbers has measure 1, but the set of transcendental numbers which are super well approximated by rationals in this sense has measure 0. So it's still a really tiny proportion, but nonetheless, it does at least show that there do exist transcendental numbers. And we'll see a little bit more about that towards the end. We're going to quantify how something called the irrationality measure of a number, which tells you for this number in particular, for Liouville's number, you get infinity. It's somehow infinitely irrational. It's as far away from, so because it's super well approximated by rationals, it's sort of infinitely irrational. It's kind of a little bit of a weird thing, but okay. So as Joy points out, there's an earlier approximation, which, so 22/7 I say because, 22/7 I say because I think that's the one that a lot of baby boomers used when they were growing up. Baby boomers and engineers, especially from the baby boomer generation, used 22/7. You can go back to the Bible and you will have 3 is an approximation for pi. And some of the others may not be so familiar. So there's 333 over 106 is one of them. And 355 over 113 is the next one. And then the next one is massive, like has massive digits. So you might have seen some of these numbers show up. And in particular, 22/7 is a very good approximation, like better than it deserves to be. 355 over 113 also is a ridiculously good approximation. And let me give you some sort of intuition for why that is. So, and in the first case, what is the first approximation? So the first approximation is just, I take this 3/1 and I see, okay, well, I have this 3 plus some remainder, right? So I can write pi equals 3 plus something. I'll write x1 maybe, where 0 is less than x1 is less than 1. Now, if I write, so now if I think about x1, I want to approximate that by a rational number, but it's between 0 and 1. So what can I do? Well, what I can do is I can flip it. I can take its reciprocal. So when I do that, I have that 1 over x1. It turns out to be 7 point something, right? 7 point something. So I think about this as 7 plus x2. Where 0 is less than x2 is less than 1. And so what that means is that, a pretty good approximation would just be, well, x2 is relatively small. So I can take pi to be equal to, or approximately equal to 3 plus 1/7, right? And that's where we get the 22/7. But I can keep on repeating this now. So x2 is some small number, and I can think, oh, well, 1 over x2, that turns out to be 15 point something. 15, I don't want to write exactly what it is. It's not what I just wrote anyway. 15 point something, so it's 15 plus x3. And so in the next approximation, I had pi is about, remember, 3 plus 1/7 plus this little bit extra, which is 1/15. And in the end, I get this sort of infinite approximation for pi. I get 3 plus 1/7 plus 1/15 plus 1/1 plus 1/, and then the next one is ridiculous. It's 292 and some other things. So why are some approximations really good? Well, some approximations are really good because if I think about, say, let's suppose I stopped at 22/7. So I'm now pretending that this bit is 0. Well, that bit is almost 0. It's 1/15. And 1/15 is really quite small. So just stopping there is already a very good approximation. And what you'll notice is that, anytime that there's a large number which comes next, so if I stop right here, I have this 292. Well, 1 over 292 is a really tiny number. And that's why I was saying that 355 over 113, which is the fourth number that I get, just coming from considering 4 of these elements in the so-called continued fraction expansion, that number being very large means that the approximation is very good. And the statement that I want to make, I know I'm kind of running out of time, so I want to get to the punchline. The statement that I want to make is that to check how well approximated a number is by rationals, these continued fractions that you get, they're called Diaphantine approximations. It actually suffices just to check how good these are. So it suffices to check how good these Diaphantine approximations are. Yeah. So as somebody pointed out in the chat, Notabot, that 355 over 113 minus pi is about 2 times 10 to the minus 2 to 3 times 10 to the minus 7. So even though you have a denominator of 1 over 113, a denominator of 113, you're getting about whatever, 5 million, like 1 in 5 million, whatever. And Joy points out exactly what my next point was, which is that the worst approximated, so the worst approximated number would be 1 plus 1 over 1 plus 1 over 1, and so on. And that is 1 plus the square root of 5 over 2, which is the golden ratio. And 1 over square root of 2 that we used before, which we said was poorly approximated, is 1 over 1 plus 1 over 2 plus 1 over 2 plus 1 over 2, and so on. So it has a lot of 2's in it, so it's not particularly well approximated. So the last thing that I wanted to say, which I really wanted to say as kind of a punchline, is that there's a definition of irrationality measure. So if x is in R, we define mu of x to be the irrationality measure. Is the maximal number, mu, such that there exist infinitely many rational solutions with, x minus p over q is between 0 and between 1 over q to the mu. So, just as an example, if x is rational, then mu equals 1, right? And you might say, well, rational numbers are sort of perfectly approximated by rational numbers, but it's sort of a convention to include the 0 as less than symbol here. just that's sort of a convention. And what we showed is that if X is algebraic, then what we must have is that mu is less than or equal to d, where d is the degree. That's a rephrasing of what we stated before. And what it turns out is there's a theorem called the let me get all the names, Siegel-Roth, I think, which is hard, which actually says that if X is algebraic, then mu of X is actually equal to 2. So whatchamacallit. So it might seem like whatchamacallit. What do I want to say? So the higher that mu is, the better approximated by rationals that you are. And this is some statement that actually algebraic numbers are pretty poorly approximated by rational numbers. However, you know, if X is transcendental, then mu is greater than or equal to 2. And, you know, as two examples, one can compute that mu of E is equal to 2. So E is pretty poorly approximated by rational numbers, whereas a rephrasing of what we said before with regards to Liouville's constant is that mu of lambda equals infinity. So, so anyways, there's this notion of irrationality measure. Maybe I should remark that mu of pi is currently not known. So it's less than about 7.1, and you know, it's greater than or equal to 2 because pi is transcendental, but nobody actually knows what value it is currently. So so Joy points out that the Taylor series expansion for E is the sum over 1 over k factorial, but there's a result due to Euler, which is that if I look at the continued fraction expansion, oh gosh, so it's going to be 2 plus 1 over 1 plus 1 over, I might get this a little bit wrong, but hopefully I'm right. 1 over 1, 1 over 6, and so on. Where essentially, if I just read off these numbers that are appearing, they're so 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, 1, 10, and so on. So the actual numbers in the continued fraction expansion are not getting so large. They sort of get large linearly. And because they get large linearly, it turns out that you can check that the continued fraction expansion is sort of good enough to show that the irrationality measure of E is 2. I know it's 8:26. I don't want to say too much more, but I do want to say that one last remark is that this also has sort of geometric implications. So if I look at the sum from, sort of calculus type implications. So if I look at the sum of cosine to the n, cosine of n to the n over n, and I ask, does this converge or diverge? The answer is actually that it converges. And the reason why has to do with the fact that pi has a non-infinite irrationality measure. So mu of pi is strictly less than infinity. And the reason why that matters is because that means that if I look at n minus pi, this is actually relatively large. Is sort of large with respect to n. So the fact that its irrationality measure is non-infinite means that n minus pi will never get too small. And it turns out that that's exactly what you need to prevent cosine of n from getting too close to 1. Because if you have a 1 too many times, then this thing will diverge. And so you end up getting this remarkable fact that understanding irrationality measures of a number like pi can tell you when these tricky sort of sums converge or diverge. Okay, so I know I'm out of time, so I will leave it there, but I'm happy to stick around and answer any questions that anyone has. I should say that there's a lot more to say. So I wrote like, I don't know, 8 pages about this, and I can send around what I wrote to anybody who's interested. Just feel free to email me, and there's a lot more information. Okay, thank you.
Oh, you could send that over to us, and we could put it on the website if you'd like us to.
Oh yeah, that sounds great. Yeah, that'd be great.